In this tutorial, we're going to learn how to determine reaction yield using chemical stoichiometry, and that's simply a term used to help us determine how much of a product can be made from a particular amount of a reactant, or how much of a reactant is required to react with something else to form a given amount of a product. Very similar to a recipe if you're reading the box and it tells you how many servings it will make. Depending on how many servings that particular quantity will make, you may have to double or triple your recipe, or maybe even use half as much. So these particular coefficients here and these formulas actually do act like a recipe, where our units, rather than being cups and teaspoons and tablespoons, are actually in units of moles. And these red numbers, of course, represent our coefficients in the balanced equation, and they represent the number of moles of each reactant and product. So we can actually say every 2 moles of methanol are required to react with 3 moles of molecular oxygen. And that in turn will produce 2 moles of CO2 and 4 moles of H2O. You could also say that every 3 O2s will produce 4 H2Os. And again, these values being in mole units. So you could say 2 moles of methanol will produce 2 moles of carbon dioxide. So it's a 1-to-1 ratio. So if I had 10 moles of methanol, I would produce 10 moles of carbon dioxide. Very similar to, again, a recipe. So what we can actually then say is that these equivalencies of 2 to 3 and 3 to 2 or 3 to 4 actually are conversion factors. And just like dimensional analysis problems, they can be used to help us predict reaction yield. Let's take a look at an example down here. And this example asks that if 4.5 moles of methanol are consumed in the combustion reaction above, then how many moles of water are produced? So we could actually look at the problem and say, okay, methanol to water, every 2 moles of methanol, okay, produce 4 moles of water. So we make double the amount of water. So if we have 4.5 moles of methanol, we'll make double that of water, or 9 moles. And there's our answer, 9 moles. But it's not always easy to do this in your head, so we should go ahead and solve this problem using dimensional analysis so that we can learn the proper technique and therefore be able to solve any problem, regardless of how simple or complex it is. So our conversion factor is 2 moles of methanol is equivalent to 4 moles of water. That being said, the given amount was 4.5, so 4.5 moles of methanol. Again, write the given unit. There's the given unit. Multiplied by your conversion factor such that the given unit is there on the bottom and diagonal, so it will cross out, leaving you with the desired. So what's our conversion factor? 2 to 4, where the 2 moles of methanol will go on the bottom, so they line up with these moles of methanol, and that is equivalent to 4 moles of H2O. So 2 moles of methanol to 4 of H2O. 4.5 times 4 is 18, divided by 2 is the 9 moles that we were able to calculate in our heads. Let's move on to then a little bit more of a complex example. And here is one where we take aluminum, iron 3 oxide, and produce aluminum oxide and molecular iron. Alright, so in this case, I've actually set up a table. And again, this is just like a recipe where you have 2 moles of aluminum reacting with 1 mole of iron 3 oxide to produce 1 mole of aluminum oxide and 2 moles of iron. And so if our recipe was all in units of moles, we would have no problem. If our questions or our calculations were given in the problem as moles and asked for the answer in moles, then we wouldn't need to look any further. But just as in recipes, sometimes we're not asked to measure in cups and tablespoons, but we're asked to count egg yolks and weigh ingredients like weigh the amount of flour in grams or a pinch of salt. So we are going to have to use different units. And in our chemical recipe, we only have 2 choices. We can calculate using moles, which we just learned how to do, or we can calculate using grams. The reason why we have both is that it is actually more practical to write a chemical reaction or a chemical equation in terms of mole values in a balanced equation. So that's how you'll see it in a lab manual, in a journal, or in a textbook. But in the lab, it doesn't translate as well because our scales don't read in mole values, they read in grams. So we need to be able to go between moles and grams because moles are practical for writing and grams are more practical for use in the lab. So it just depends. If you're given moles and ask for moles, you'll use moles. If you're given grams and ask for grams, then you'll use grams. And we have set up this table so that we can look at how many moles are in this recipe and how many grams are in this recipe. And the reason why we do that is just so that we have every number lined up and all our conversion factors ready to go, so that when we are ready to start solving the problems, we don't have to stop, go back, and perform little calculations and pick up again with the problem. We can start and just pick values that we need and continue going through the problem. Again, going with our analogy, it's just like when you're cooking and you have everything chopped up and ready to go, like on television, and you can just take your X ingredient and your Y ingredient, add them together and just keep going rather than stopping to chop your onions and then stopping to chop your celery and stopping to measure your eggs. You can just have everything ready to go and just start adding them together, and that's what we're doing in this table. So I have, of course, the equation and moles and grams. So, of course, we have 2 moles of aluminum. So in the moles category under aluminum is 2. I have 1 iron 3 oxide. So under moles, I have 1 of the iron 3 oxide. I have 1 aluminum in the equation. So that's 1 mole of aluminum in the table. And 2 moles of iron. So that's 2 moles of iron. Now I'll look at the equivalencies for that in grams. So what is the equivalence of 2 moles in terms of grams? 2 moles, because that's what this number is up here. So I'll look up the atomic mass of aluminum on the periodic table. It's 27 grams. So 2 of those would give me 54 grams. 54 grams is the equivalent of 2 moles. So depending on which value I need or which unit, I now know exactly what number to use. Same thing, iron 3 oxide, only just 1 of them. So what's the gram equivalent? 2 moles of iron 3 oxide, just 1 mole here. I'll take the mass of 2 irons, the mass of 3 oxygens, add them together to get the formula weight, and that comes to 159.6 for each one. And I only have 1, so there I go. Do the same thing for aluminum oxide. The mass of 2 aluminums, that's 54. A mass of 3 oxygens, that's 16 times 3 or 48. Add that all together, and that is 102. 102 grams for every 1 mole. Last but not least, I have 2 moles of iron, so I'll look up the atomic mass of iron on the periodic table, multiply by 2, and that is the equivalent of 111.6 grams of the iron. So I have everything ready to go, and now I can start solving my problems. Let's take a look at this example. It asks that in this one process, we have 124 grams of aluminum, and they are reacted to form aluminum oxide according to this equation. How much aluminum oxide is actually produced? Well, let's take a look. Let's write our given just like we always do with a dimensional analysis, and that's 124 grams of aluminum. Then we'll look to see what our conversion factor is between aluminum and aluminum oxide. So we're looking for grams first and foremost, not moles, and we're looking for aluminum, which is 54, and aluminum oxide, which is 102. So there we go. Every 54 grams of aluminum is equivalent to 102 grams of aluminum oxide, whereby the grams of aluminum will be on the bottom to cancel this one out, and the 102 grams of the aluminum oxide will be on top. 124 times 102 divided by 54 gives us 234 grams of the aluminum oxide produced. So you see, when you have the numbers ready to go, it's quite simple. Now, we went ahead and wrote this table for mole values and gram values for every reactant and product, just for practice sake. But as you can see, if you only need gram values and you only need it of 2 of your compounds, then by all means, all you had to do was calculate the equivalence of the aluminum grams to the aluminum oxide grams, and that's all you would have needed to solve this problem. So you don't have to take the time to set up and calculate this entire table for each and every reaction and problem that you'll encounter. But we just went ahead and did it in this particular example for practice sake, but certainly no need to do that on a regular basis. Now the next thing we want to discuss is something called the limiting reagent problem. And a limiting reagent is the reactant that is basically going to limit the amount of your product that you're going to make. And the reason why and how it limits how much you make is because you run out of it. That reactant is consumed in its entirety in the reaction. And once you run out of it, of course, the process stops and you can't make any more product. So in the case of the same reaction here, once let's say you run out of aluminum, you can't make any more aluminum oxide or iron. Why? Because there'll be nothing left to react with the iron 3 oxide, and vice versa. So the only way to determine which is the limiting reagent, and therefore exactly how much product you're going to make, is to solve the problem for every single reactant amount given. So let's take a look at this problem. It states, in one process, 124 grams of aluminum are reacted with 601 grams of iron 3 oxide. Okay, so now we know how much of the iron 3 oxide we also have, and they indeed form aluminum oxide according to this reaction. What we'd like to know is, now, given this new information, the second reactant amount that we have, and that's a hallmark sign of a limiting reagent problem, is when you're giving two different amounts, how much of this aluminum oxide are we going to produce? We have to solve it both ways for both reactants. There's the 124 grams of aluminum that we've already calculated using the conversion factor of 54 to 102 that produced for us 234 grams of the aluminum oxide. Let's see how much this 601 grams of iron 3 oxide will produce. Here's the conversion factor. Where am I getting the 102 and 159.6? Looking right here, 159.6 grams of iron 3 oxide produces 102 grams of aluminum oxide. So there's where I'm getting my numbers, because those are the two compounds I am dealing with in this problem. So 159.6 grams of iron 3 oxide is equivalent to 102 grams of aluminum oxide. The iron oxide will be on the bottom, so they cancel out, and 601 times 102 divided by 159.6 will give us 384 grams of aluminum oxide formed. So we had two reactants here. We solved it for two reactants. If we had been given 3 or 4 different types of reactants and amounts, we would have had to solve this problem 3 or 4 times. So you're going to have to solve it each and every time. The answer that you will report at the end, however, is the smallest amount. Why? Because that is the amount that is practically or realistically made, and it comes from your limiting reagent. So in this case, which was the limiting reagent? The one that made less. That would be aluminum. And we would then report the amount that was produced by the limiting reagent, which is 234 grams. Why? Because theoretically, we could have made 384 grams of aluminum oxide from this 601 grams of the iron 3 oxide. But here's the problem. We ran out of aluminum before we could do that. We ran out after 234 grams were made. So theoretically, we could have made it, but we ran out of aluminum, and right after the 234 grams were made, the reaction stopped. And that is the correct amount that you would report as the answer to this problem. And this other amount is simply in theory.